Good day. My name is Vikesh Rampasad. I'm a student at UNISA. My student number is 159358868. This is my project for transportation engineering, pavement and geometric design. Uh, this is assessment 2, which is a project. For this project, I have chosen to do a upgrade of a gravel road to a surface road, which runs from D35 to D41. The brief was for me to design a road, and it should be comprehensive with regards to structural design, geometric design, conceptual design, and of the stormwater drainage system. And I'm supposed to generate detailed software generated drawings, which should have a design report in PDF format. The aspects we should consider should be the safety, efficiency, environment, and the economy of the description of the road. This road is approximately 4 kilometer long road in the city of Dithakong. It is part of the Joburg local municipality, and they also the authority of that road. The existing road is a gravel road. It's a 2-lane. It's moderately trafficked, and forms an important link between two class 3 roads, which connects at its eastern and western ends. The road starts on the eastern end at Chinese 0 and goes all the way to Chinese 4313. There is a culvert, there's a stream, the existing road transverses via culverts, and this is at approximately Chinese 420 and 460. It also forms part of the routes to the primary school and a church, and it gives access to individual urban. There are existing services in the form of existing overhead electrical services located on the northern edges of the road reserve. There is a Google map image showing the locality of the road, which shows the eastern and western extremes of the road. There's a water stream that it shows the primary school and the location of the church. That is the existing profile of the gravel road. There's a snap again with Google Earth viewed from Road 41. That is the stream which the existing road transverses or crosses. Overview of the design process which I followed was to get a brief from the client and then to collect data which is required. I would first do the structural design of the pavement using TRH4. After that, I would do geometric design of the pavement using TRH17, followed by a computer-aided geometric design. I would do manual checks on a certain aspects of the geometric design. I would also confirm my manual checks with Excel verification. I would also do a drainage conceptual design using TRH15, and ultimately I'll produce design drawings. The client's brief, it was supposed to be structural design period of 15 and analysis periods of 25 years was confirmed. The road is classified as an interurban collector and has been classified as a Class B road. Its equivalent classification according to TRH26 is a Class UB4 urban residential collector street. Climatic region is moderate. The design data, existing data source from the client is ADT, annual average daily traffic of similar roads, data procured from other specialists in the form of LiDAR topographical and existing services surveyed by a registered surveyor. Centerline CD subgrade DCPs by registered geotechnical specialists and then test pits and so on indicated tests by registered geotechnical specialist. Design standards for the structural design I used, which was TRH4. The data, these are the data that I use: the structural design period, the climatic region, and the average daily traffic. And the centerline DCPs were converted to equivalence CBR values. That is the analysis and projection of the traffic. After doing that, so more than 2 million E80s per lane was required, and this made it in a pavement class of ES3. The in-situ subgrade is an existing gravel road. The CBR values all exceeded 15%, therefore the entire length of the road was seen as subgrade area 1. And for this, that required it to be ripped and recompacted to 150 millimeter G7. That's the subgrade preparation. Using the TRH4 catalogs, various options for this road and this road category and this class road was was considered. There was a granular base design, hot mix asphalt base. There was cement treated base. There's a water-bound macadam bases were considered. Availability of the materials were and unit cost price were, were sourced. Everything was available, and these were the cost prices. A cost comparison was done to determine which was the most cost effective one, and this was the basis for our selection. At the end, ultimately at the end, option 3, which is the cement treated base, was chosen, uh, which is a selected surface layer S surface layer, a base layer of 125, which is cement treated C3, sub base layer of 200, which is cement treated C4, and then as we said, the in situ subgrade would be ripped and recompacted to 150 millimeters to G7 standard. Then the next thing I did was to the geometric design of the pavement, applying TRH 17 and 26. Uh, I had, out of those, I sourced the various inputs. Example, minimum radius, design speed of the road, and maximum length of the gradients, and so forth. That was, and then also for the vertical alignment, same thing. Out of the TRH 17, I got the various input parameters which I was going to use in Civil 3D, as well as the transverse alignment was also designed in accordance with TRH 26. I then decided what I decided on this was my typical transverse alignment, which I had settled on. The existing road reserve is 30 meters, which is in compliance. I had side drains either side with a road cambering, with pavements, and with a side with sidewalks and side drains either side. Uh, After that, I went into Civil 3D, and this was basically the software aided geometric design which I followed. These are the steps from the coordinate system to creating, applying design criteria to the alignments and profiles, and then ultimately generating the drawings. I'm just going to jump through Civil 3D now, so we can have a quick look at what was done. Uh, okay, so that is the road which I was designing. There's a horizontal alignment. I checked and put the design criteria file there to it. I checked for compliance. Same with the vertical alignment. Did a check the compliance with those standards. That was my transverse section, which I in compliance with TRH, which I used as a sub assemblies and assemblies, and then ultimately I generated. That's a 3D model which was generated from those horizontal alignments and vertical alignments and transverse sections. That was the layout of the road. I then took sample lines at 40 meter intervals, and then which generated my cross sections at those intervals. There, I created a road, a datum level, and a top level, which enabled me to calculate the volumes, cut and fill volumes, as I progressed around the road along those chainages. Additionally, after having done that, I optimized the design using and looking at the mass hole diagram. I applied a free hole value of 1,000 kilometers, I believe, and I think in red is the overhaul, and in blue is the free hole. I just generated the total volume tables to see that it is optimized. It seems quite fairly optimized, fairly balanced cut and fill, which has obviously drives down the cost. I then used setting out tables. I generated setting out tables, and then after that, I then proceeded to plot the drawings, the mass hole drawings, the cross sections, as well as the planes. Next, I did manual checks on the curve. I checked the adequacy of it with regards to to the super elevation and the minimum ranges, as well as the coordinates of the beginning and end of the curves. Um, I then verified it using Excel, to verify it, and those are my that is my Excel verification. Next, the conceptual design of the road is I use the TRH15 and TRH4 for the conceptual design. The side grades which I had, the vertical grades exceed 0.75%, the campus and of 2%, and shoulders are paved, and this allows drainage to the side drains. The road reserve also slopes towards the side drains, and which would ultimately drain the road reserve. Subsurface drainage, no subsurface drainage is required because the in-situ soil was classified as free draining with a water table below the material depth. So overview, side drains on either side of the cambered road will drain the road itself, and as well as the road reserve. Portal culverts were used with relevant headwalls to transverse driveways. The side drains ultimately discharge directly in the stream at plus minus drainage 460 via headwalls, where the road transverses the existing stream at drainage 460. Precast portals are used as bridges 10 to height, which ensures it is above the 1 in 100 flood line. Results: the whole road will be upgraded to a flexible pavement road. Pavement options were considered, and the cost-effective one was cement treated base. The road transverse section was cambered with shoulders and as well as sidewalks and side drains. No bicycle lanes were provided in accordance with existing estimated non-vehicular traffic and surrounding network. Road markings and signages as well as traffic combinations was provided as indicated on the drawings. Vertical and horizontal alignments are all in accordance with the guidelines. And then we spoke of the drainage with the side drains and the culverts which crosses the accesses and discharging into the stream itself, and the portal culvert used as to bridge the existing drawing. Next, I'll just show some drawings. These are the final produced drawings. That's the plan and the setting out table. These are the cross sections, and that is the mass hole diagram. So recommendation, I recommend that routine inspection and timely surface maintenance must be implemented, restored and implemented to restore a deteriorated surface, which should last until the structural design period of 15 years. This will prevent early structural failure and ensure the pavement is functional for the analysis period of 25 years. Another thing I need to mention is that at the school, on my drawings, it shows that there is provision of bus bays and raised intersections were made for safety and for access to the church and the primary school. These are the references. The full report is obtainable from myself. Thank you very much.